Okay, so hello everyone, and sorry for being late. Uh, uh, so I want to ask, do you have any questions about the problems I gave before and I did yesterday, and about the previous lectures? Uh, okay, so let us maybe start then. Uh, uh, so let me remind what we learned the last time. So the last time we studied the equation du over dt equals Laplacian of u, and we can solve this problem with some initial conditions, like u of 0x equals to 0, and minus Laplacian equals to f. To f of tx. And the solution of this equation was u of tx equals to integral minus infinity to plus infinity e to minus x minus x prime squared over 4t 1 over 4 pi t to d over 2 u 0 of x prime. Yes. Yeah, maybe better to write not multiple integral, but just R2D. Right. Plus, so this was a initial initial value gain function, and there is also another integral for the right hand side. So it's integral d plus 1 and something maybe let me write it using heaviside theta over 4 like this. We can actually add some coefficient here. We can write kappa in front of the Laplacian. And then let us see what changes. Well, actually, I had to do this from the beginning, but effectively it can be moved to t, so it will be modified approximately like this. So here it is obvious. Here as well. Here we have kappa, and here we should be a bit careful, maybe. Oh, maybe. No, maybe it is fine as written now. Yes, because this one uh, turns into a delta function anyway, independently from kappa. Uh, so, uh, but what I want to discuss is what happens when kappa is less than zero. So here we see that this problem has a solution which exists for more or less any initial conditions and any right-hand side because it is super easy to get convergent integral unless we impose some huge growth rate for this function at infinity. So, this problem is well posed. And the question is, what happens? Uh, hmm. So let us. Uh, um, so here kappa is greater than zero, and in this case everything is fine. So are there any questions at the moment? Yeah. Hmm. Where? Mm. Mm. No, could you say it again? Uh, eh, you mean this coefficient? Let me think. Sorry, maybe you're right. Mm, so. Mm, mm, Uh, no, wait, there is this function. How to write this equation? So d over d t kappa minus Laplacian uh, acts by zero on this function. Uh, equals to delta. So do you agree with this? So it's in this function which solve this equation. So if you multiply it by kappa, it will give kappa in front of Laplacian. So this is how I get this. And to get overall factor, I just checked that it is a delta function when t goes to zero. So there should be no other factors. Mm. Hmm? But it's it's a good question. But here it does not matter because kappa is greater than zero. Yes, but it does not make sense to compute analytic continuation of this function in a kappa to this negative values because, for example, it can give imaginary values for well, if you insert kappa here, then it will be fine. Well, yes, uh, yeah, in principle, it might make sense. But anyway, I don't want to add this again function uh, for this mm, other problem because of course we can consider evolution the negative time and ask not for the initial values but for the finite values, and it will be exactly the same problem. Uh, well, yeah. Mm, no. Why? Ah, so let me think actually. Mm, so you're saying there might be some power of kappa here, right? Mm, let me think. Mm, no, I don't think so because I remember this argument like how to get do you agree that this first part is this one without any extra corrections? Yep. Because this turns to a delta function and it actually gives a solution with this initial condition. And then we can remember this argument that this green function can be obtained from this one if we just uh, put f equal to a delta function of t at some moment of time infinitely close to zero from the negative side. And so if we do this, it will give us the value of this green function for t prime equals to zero. And we should recover precisely this function without any prefactors. But you don't need, you can change the initial condition, then you will need to change integration variable and so on. But I think all this will reduce to this formula. because of this argument that if we substitute here the delta function times u0, it should give us this formula, and we check that precisely with this answer without any factors, it gives precisely this integral. So, or maybe it's homework, because there is this argument, but you can compute this explicitly. So. Yeah, so can I go start? Let me actually check that it's working. So when kappa is less than 0, let us switch to the Fourier components. So in this case, we have u equals so we switch from u of t and x to some u tilde of t and k. And Laplace equation turns into du over dt, du tilde over dt, minus let us just put kappa equals to minus 1. Maybe no, let us write it for arbitrary kappa. Minus kappa minus kappa Laplacian k times u equals to 0. And we know that and we have initial condition that u tilde of 0 k equals to u 0 tilde of k. So a solution of this equation is, of course, okay, is u of tk, u tilde of tk equals to e to kappa Laplacian of k u tilde 0 of k. And now there are options. So if let me think. Yes, thank you. So now there are different options. Like if x is in some finite domain, maybe it's the same. If it is one-dimensional or multi-dimensional, then this eigenvalues, they're always negative. They equal to something minus minus 4 sum of sine squares of k squares k I. if it is a finite dimensional case, everything is fine, and the phenomenon which we see here is the following. These two numbers are negative, so when we send t to infinity, this evolution amplifies the modes with the highest possible with highest possible wave number, with highest possible value of this sign. So it means that if we take any non-constant function as the initial value, in the limit we will have a function which oscillates as quickly as possible. And it is some indication that if we switch to a continuous limit, we will have some problem. Mm. So maybe it's better to write it in terms of in integer numbers. So don't know precisely like pi k I over n. But it's finite dimensional problem. We can only see that something bad happens, and don't understand what it means in the continuous limit. So if we consider x, which is on the on just integer lattice, then so here the ki's are integer, z over zn. If x is on the integer lattice, then this eigenvalues of Gaussian will be of the same form. In this case, now will be from 0 to pi. So here we see again that it's not a big problem. We'll just take the term. So the leading contribution will correspond to this ki's i's maybe ki over 2. Correct to say. Ki is equal to pi, which will correspond to anti-periodic function. So this mode will be amplified. But so it was for discrete cases where we cannot get singularities. And if we switch to something continuous, for example, when x is in S1, then this delta case delta case will equal to minus sum of ki squared. And these ki's are integers. or if this x is on a real line, so S D, maybe Z and D, Z over Z and D. If x is in RD, then eigenvalues of Laplacian will be well, actually it will be the same, but with a real k. Hmm? Yes. Thank you. S1 to D. Thanks. So let me remind that in this S1 case, this U of who is first T and X equals to sum of U tilde T X T K e to the I sum of phi I K I. And so this is 1 to power D. There is this Fourier transform, and for R to power D, U of Tx is a integral dk over 2p pi to power D the tilde of tk e to the I k times x. So here the size from 0 to 2 pi. So and it's periodic in phi. So and if U is continuous, what is the restriction on the Fourier coefficients? So may I raise this? Maybe it's better. Oh, well. So as I remember, we can integrate this by parts and obtain a statement that these coefficients tilde of tk are less than, well, in this case, maybe 1 over product of k1, kd. It's not very nice expression, actually, but let it be. So the point is that if we have some continuous function, this coefficient should decay somehow. And also, if we want to be able to compute this integral, there should be some restriction on this coefficients, because even if it is even if the integral is absolutely divergent, we should be able to compute this. Uh, but the problem with this function, which you get in this way, is that for this continuous cases, this u tilde of tk equals to e to the t e to the minus t kappa. Sorry, I should write it through. u tilde of t and k behaves like e to the minus t kappa k squared u0 tilde of k. And this product minus t kappa is positive. So this evolution, even in a very short time, multiplies Fourier modes of our initial function by something which grows in scale very fast. And it means that the right-hand side is not well defined. Usually. The only way to make it well defined to make it Fourier transformation of some well-defined function is to take initially something very, very smooth so that its Fourier modes decay faster than e to arbitrary number times k squared. Mm, and if add any small perturbation to this initial condition, then we will have a problem. And mm, so mm, uh, uh, so we can take u0 of k equals to, like for scalar function equals to e to the minus k to the fourth. Actually, don't remember what it is in the coordinate space. Probably it is a Bessel function with some index like 1/3. So I don't remember, but it's computable. We can get a coordinate representation. But we can also think about this in some other way. So, for example, let us take our green function, like this one. We know that it solves a heat equation for t greater than 0, and if we now just we can forget about this factor kappa here. I know, so I think. Yeah, so let us take this green function as the initial condition to this heat equation with the wrong coefficient. It looks like a normal initial condition, and its Fourier transformation, as we remember, will be precisely e2 minus some coefficient times k squared. But since it is now multiplied by positive k exponential, it will change this coefficient basically to decrease the time. in this formula. And at some moment we will hit t equals to 0. So it means that if we run this heat equation with a wrong coefficient, it will be equivalent to evolution in the opposite time. And there is an example, this kind of function, of a function which turns to a delta function in some finite time. So if I take this as initial condition in some t with an infinity, we can get a delta function. So this solution can develop singularities. So is it clear? So and this corresponds to u0 of x is e to minus a x squared. So is the argument clear? So it happens when in this case you so this one it's for a transformation is e to minus k for a probably this one times some coefficient. So what is the value of t0 for which the solution develops singularities? What is the value of t0 for which we can get delta function starting from this initial condition? No. So you see, our original utility 0 is this e to minus k squared over 4a, and utility of t is u0 multiplied by e to minus t kappa k squared. So this happens when minus k squared over 4a, which is originally here, minus 4 minus t kappa k squared equals to 0, which means that t0 is minus 1 over 4a kappa. Is it okay? What happens after zero? Maybe, well, maybe it does not make sense to ask this question, because after this moment, this exponential, well, after this moment, we will have e to some positive number times k squared. And this Fourier integral, which in principle should recover u of x, for us will be divergent, and there is no way to make sense of it. There is no way to compute it. So the solution just terminates at this time. Hmm? Kappa is negative. Precisely. It's literally a heat equation backwards. So, hmm? uh, what do you mean? Y- Yes. Yeah, if you think the other way around, if you take heat equation and try to run it back, you will be able to go in general position not longer than the time of initial evolution. So we can recover initial conditions, but after this, there is a high chance that it will blow up this way if initial conditions were not smooth enough. So. Mm. It can happen either at some finite time in the past or literally at zero. Mm. Yeah, so in this example. Mm. And I actually wanted to show two more examples where problems can be either well posed or not well posed. So, mm, other examples. Uh, Wave equation versus Laplace equation. So let us consider, uh, mm, mm, maybe I can split this blackboard into two parts. And right here, uh, uh, so let us consider such a rectangle of width L and length T, and the same here, X and T. And so 0. And let us consider here the equation d square u over dt squared minus d squared u over dx squared equals to 0, and uh, mm, u of t0 equals to u of tx equals to 0. So there are boundary conditions. Uh, no, it's boundary conditions. TL. So it's boundary condition. And the same here, but with opposite sign. So I'm not writing any initial or boundary conditions in the opposite direction, because this is precisely what we are going to discuss. So here we can again perform the Fourier transformation in x coordinate. So we switch from u of tx to u tilde of tk. Here the same, u tilde of tk. And this equation now has a form d2 over u tilde over dt squared equals to maybe plus k squared u tilde equals to 0. In this case, it is d2 tilde over dt squared minus k squared u tilde equals to 0. Mm.
Which kind of transform are we performing? The one on S1? Because we have found
No, it's not S1 because it equals to 0. So we should use this sign for a transform, namely, so u of tx is sum of u tilde of tx tk sine of kx when k is in pi over pi over maybe how to write it better, pi over L z greater than 0. So in other words, k equals to pi n over L, n equals 1, 2, and so on. So this basis of functions is like this. The first function is sine of pi over L. Second function is sine of 2 pi over L, and so on. Right? So we had this this example or similar example for the finite set of points, but there's always generalization to the infinite also. Pi x over L, 2 pi x over L. Right. So it can be obtained from antisymmetric functions or on a circle. So. But the important point is that this k can be arbitrarily big. So and now how to solve this equation? So at this moment we have another kind of splitting because we can either say that there are initial values or there are boundary conditions. So if you consider initial values, uh, we need to say that u of 0 x equals to u0 of x, and u of u ut, time derivative of 0x equals to some u1 of x. So if you consider this, then we can immediately solve this equation in the following way. U tilde of um, tk equals to, by the way, who can, u0x is yes. Is it okay if I use this notation or not? So maybe. So ut is by default du over dt. Yes, so if we have these initial conditions, who can write down the solution for u tilde? Like, what is the general solution of this equation? If you choose some real basis. Yes. So mm,
0x times cosine of kx.
tilde.
Yes.
Cosine of k. Yes.
Plus u1 tilde sine of
Not quite.
u1 tilde divided by k.
Yes. Thank you. So everything is fine. Mm. So when is tilde of k. So we see that if this u0 tilde and u1 tilde are Fourier coefficients of some nice function, it means that they decay at the infinity, and we multiply them by some functions which are bounded. So it is this function will be good at any value of t. So everything is perfectly defined. We found the solution. That's all. Now let us try to do the same thing for uh, for Laplace equation.
Sorry, just one last question.
Mhm.
What about boundary conditions in this case?
But we will. So, do you want to start from boundary conditions?
No,
Like,
no, just because we started from boundary conditions at the beginning, so I was wondering.
ah, you mean this? So,
Yeah, yeah, you see.
ah, also, so here there were boundary conditions at the left and at the right, but here we can try to impose the same kind of conditions at initial and at finite finite time. So let us check what happens. So let us check what happens if you ask u of 0 x to be u0 of x, and u tilde of t, oh sorry, u of tx to be some ut of x. So who can now write a solution for this equation with this boundary conditions? So suppose that we know for a transformation of these two functions, like maybe someone else who can solve it. Ut of k and k equals to
Maybe you can just mention UTX to UT0, so to U0x, and so we get U0 tilde k times cosine of k, and maybe the sine of t minus
uh, so no, if you add another function of this kind, it will break this boundary condition.
So plus u tilde t, okay. Okay, times the sine of k times
Yes, probably. So if you want to have it, if you want it to equal to this one, and that boundary, you should probably divide by sine of big T, okay, right? So it turns to one on that on that side. But not only this. Uh,
minus u tilde 0 k cosine of big T capital T k.
yes. Uh,
No,
Probably. So we need to cancel this term on that boundary. Uh, with such kind of term. So maybe better to write like like this. So we cancel it from the very beginning. U tilde 0 tilde of k cosine of big T k sine of tk over sine of big T k. So now it should work, right? Because it turns to 1, and this cancels. And now we see a problem. In principle, it can easily happen that tk equals to pi. Or tk can be close to pi, and if we increase k, it can jump closer and closer to pi. So we see that in a general situation, it's not fine at all. Uh, because 1 over sine of tk divided because tk can be uh, 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 close to a pi some integer number. So either equal to pi times integer or close to. And also we see that since there are many such cases, so what this problem really means? So we say that it equals to pi times m. So let us write this condition precisely, that t times k and k are pi n over l. Mm, no, maybe a little bit run out of the blackboard. So let us actually compute the estimate between tk and pm. Because it will be the estimate of sine in the denominator. Tk minus pm equals to t pi n over l, so absolute value minus m hmm. Hmm? Yes, thank you. Mm, yes, sorry. So it will be p over pn over l times t minus m over n. Uh, yes, I would prefer to write it as no. I would prefer to write it as so pn t over l minus m over n. and we have all possible m's and n's because all n's are present because we have all these modes, and we can choose between different m's. And actually, forgot what is the uh, upper and lower bounds of this estimate. So it's some theory of rational approximations. But we see here that if Q over L is by some chance rational, then we just have some point for which this denominator vanishes, which is clear. And if it is, for example, a square root of 2, then what can we have here? So then we have Pn absolute value of square root minus m over n, and we can multiply it by square root of minus m over n times plus m over n, 1 over square root plus m over n. So these two equal to and we can find a solution. So we can find solutions of this equation, 2n squared minus m squared equals to 1 more. So there are solutions. And in this case, it will equal to what? It will equal to pi over 2 square root of n. And it will, oh no, to n square root of 2. So it means that this denominator, so it is in the denominator, so it means that this some of these terms behave behave proportionally to n. So in principle, we can take such initial conditions that even if they do not vanish identically, they will and they will go for the n, and it turns some regular solution to a singular one. So, for example, it was Originally it was continuous function. When we run this evolution, when we solve this problem, we get something discontinuous, uh, or we get delta functions. But you see, it's in any case, it's a very bad situation when your problem is sensitive to whether initial time is rational or not. The ratio of initial time and like, the ratio of two sides of this rectangle, if it is rational or not. So uh, yes. So it's this problem is well posed, and this one is not well posed. And there is also another way to understand that it is not well posed, because in this case, in 2D, this equation can be easily solved, actually. So we will see what all this means. Uh, so are there any questions about this, about the wave equation? So maybe let then switch to the Laplace equation. And try to do the same. Uh, Let us try to solve initial value problem. That u of 0x equals to u0 of x, ut of 0x equals u1 of x. So who can tell the solution of this problem? Hmm?
What can Laplace equation represent? So wave and equation
Ah, okay. So probably I had to tell this at the beginning, but let me maybe answer this question later, because I can show several problems where it appears. But for a moment, let us just study this. So. Uh, so the question is, what is u of t and x? Mm. Sorry. U tilde of t and k.
the other one, just replace the cos with cos and the sine with sine h.
Yes, thank you. So it will be u0 tilde of k cos of kt plus u0 u1 tilde of k sin of kt. And so, yeah, thank you. And now we immediately see a problem. When k goes to infinity, doesn't matter if t is positive, and No, in our case, t is from 0 to L, but it doesn't matter. So, but when k goes to infinity, both cos and sinh behave like one half of one half e to the kt, absolute value of kt. Okay, absolute value of cos and absolute value of sinh behaves like e to absolute value of k times t. And it means that if we start with some functions which are, for example, in C0 or in Cn, but not in C infinity and not so strictly bounded, then we can easily get singularities at some finite time from 0 to L. So u of x and t, t and x can have singularities. So it is a non-low post problem. So this is that it's some bad problem.
So we could see this reach from one another because we can transform one equation to the other with the transformation t to d.
Or x to x, it doesn't. Yes. Oh, so yes, it's clear that we can solve both of them and continue the solutions analytically. But the fact that we can perform a kind of analytic continuation of the equation does not mean that nature of problems to study continue analytically. I don't know what is the intuition for this. Probably it is something like these boundary conditions are given for example, for real t, but after this analytic continuation, this t become complex and something like this. So sometimes, for example, for some grand functions, this naive analytic continuation from one equation to another one work, but we should think about this carefully. We say that this, but it works not for any grand function. There should be some special ones, not very natural from such point of view. So that can be analytically continued. Yeah, so we see that this problem is not good. So it's natural to expect that another problem with boundary values should be fine. And let us check this. So as before, let us say that u0 of x, u of tx equals to u0 of x. u of L of t. X equals to u t of x. And we write this solution identically.
So the first
So,
one is u0x, right? First one, the repetition in the u of 0x.
yeah, thank you. So in this case, maybe it's better to combine such terms. So in this case, u tilde of t and k equals to what? To u0 tilde of k uh, uh, cos of tk minus this term. Uh, and, divided by what? By sinh of tk. Plus u0 plus u1 tilde of k ut of k. Actually, yes, it was uh, originally a good suggestion to use uh, 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 to use a sign of shifted argument. Sorry, I was stupid. I could write this from the very beginning. So I could write here times a sinh of t minus t k over sinh of tk. So, sorry, someone proposed this, but I didn't use this formula. So now it's much better. So and now we see that these functions do not have poles anymore, and since t is from 0 to t, from 0 to t, these functions are less or equal than 1. So this is less or equal than 1, and this is also less or equal than 1. So as before, if u0 tilde and ut tilde were Fourier transformations of some nice functions, then it is also Fourier transformation of some nice function, because the growth rate of its coefficients is not bigger than of initial function. So, so this problem is well posed. No, it is this one, because when t equals to 0, this equals to 1, and it equals to u0 of k, and this one vanishes. And when t goes to big T, this one vanishes, and this one equals to 1. It's kind of interpolation between u0 and ut. So So it's kind of deformed homotopy. One function times t and another function plus another function times 1 minus t. So here trigonometric functions. Uh, so is it fine? So. So once again, we found that if you work with the wave equation, then a correct problem to solve is to impose some boundary conditions and some initial uh, conditions for derivative for the first derivative and for the function itself. And here, the natural problem is to fix boundary values. And actually, here we can equivalently fix not the boundary values, but first derivatives. For example, we will so if you fix first derivatives, we will just need to replace this sinh by cosh, divide by k, and it should be fine. It will be the same solution, a very similar solution. And also there are mixed boundary problems when the first derivative and the function are mixed. So are there any questions? And let us look at this wave equation in more details. Try to understand why boundary value problems are not well posed in this case. So we can introduce a so-called light cone coordinates. Namely, so the idea is the following. We decompose this Laplace operator d2 over dx squared x squared as d over dt minus d over dx d over dt plus d over dx. And let us try to introduce xi, maybe. Let us introduce x plus minus equals to x plus minus maybe t plus minus x. So we can now check that d over dt minus d over dx acting on x minus equals to 2. So, and acting on x plus, it will equal to 0. d over dt plus d over dx x plus equals to 2 again. And so two other equalities. So looking at these equalities, we conclude that and this is actually a 2 times derivative in x minus, and this is a 2 times derivative in x plus. So our wave operator can be written as 4 times d squared over dx plus dx minus. Right? So uh, uh, the wave equation is then d2 u over dx plus dx minus equals to 0. Mm. And so we'll use this formula in the future. But now let us just look at this. So we can try to um, consider some other boundary problems, not on the square, but on a rhombus. So let us consider maybe not on a rhombus, but on a rotated rectangle. This is x, and this is t, and those are lines x minus t equals to constant and x plus t equals to constant. So let us consider so it will be probably L minus, and it will be L plus, in the size of this rectangle. So if you now try to fix the value of this u on the boundaries, we see that du over dx minus, so let us say that u is fixed from the boundaries. And then try to integrate this from x minus equals to 0 to x minus equals to L minus d2 u over dx plus dx minus dx minus. It will equal to d over dx plus u of x plus L minus minus u of x plus 0. And this should equal to 0. So it tells us that boundary values on different sides of this rectangle in coordinates x plus and x minus should be consistent. Otherwise, this problem will not have solution. So it's an extra condition. And we saw something like this here, because in principle, if some if some of the signs vanishes, we can try to adjust initial conditions such that this prefactor also vanish and we don't get singularity. So after all, if you have some solution, we can then look at its values at initial line and final line and pretend that it was our original problem which we are trying to solve. But the point is that we cannot do this for arbitrary initial conditions. And here this problem is even bigger, because here it depended on the ratio of T and L or something else. But in this case, we see that there is much less functions than we can expect. So we cannot put arbitrary boundary conditions for this equation. It will not be consistent. Or are there any questions about this? So let me then maybe tell a little bit about applications of these equations and where they appear. So maybe we derive something. Yeah. Oh, maybe before I erase this formulas for the heat equation, I will tell about purely mathematical application of it, namely about the heat kernel. So in principle, we can try to solve this equation in the following formal way. So du over how to say it better. So we have this d over dt equals to Laplacian times u, and this can be solved by u of t tx equals to e to t times Laplacian u u0 of x. So one way to think about this is that it is just a formal solution, just differentiate it and see the answer. And another way to think is that we can diagonalize a Laplace operator and look look at the evolution of its eigenfunctions. But this it can be So this formula then can be interpreted that matrix elements of this this formula can be interpreted as this green function is a kernel of this operator. So we can write that E of T delta kind of matrix elements x prime equal to E to minus x prime squared over 4t 1 over 4 pi t to d over 2. So but now suppose that we want to compute the trace of this operator, because in the finite dimensional case trace of trace of a matrix is a sum of a I, or maybe if our A is labeled by some points, then trace of A is a sum over x, A of x and x. But in this case, a trace of e to the t times plus n will equal to, actually it is also denoted by k t of x prime. Trace of t times o plus n equals to so from one side it equals to sum of the eigenvalues, sum over lambdas t times let us say that eigenvalues of Laplace operator is not the minus lambda case. So it equals to sum of minus t times lambda case. And so it's from one side. And from the other side, it will equal to the integral over the manifold where this Laplace operator is defined of a k a t of x. It's the diagonal element. Times actually the volume form, but let me write it like this. So, for example, even if you work with in the flat space, and our manifold is just some domain of some domain of, for example, a real plane or of some d-dimensional space, or it can be also a torus. Even in the flat space, we can ask about the number of eigenvalues of Laplace operator, or about density of the eigenvalues. So it is a TD, a dimensional torus. So for example, let us look at this case where we have a d-dimensional torus. So here we will have phi 1, we have phi k from 0 to Lk. And there is a Fourier transform. And any function u of phi is sum over u tilde k e to the I I sum of k I or k m over Lm tend to pi phi m. And we see that all these functions are eigenfunctions of Laplacian. And what are the eigenvalues? Who can tell in this? Oh, but it's a Laplace operator. It is d phi I. So yes. So I divided with the minus sign, so it equals to a sum of k for like 2 pi k m over Lm squared. So the picture is the following. For example, in 2D, we have we have some kind of of squashed lattice uh, and the eigenvalue of Laplacian is a distance, maybe like this. So those are this 1 over L integer points, and the eigenvalue of the Laplacian is a distance from 0 to a point. So if you want if you want to count the number of eigenvalues which are inside inside some circle, um, so if you compute the number of points inside some circle, it will equal to the number of eigenvalues of Laplacian less than something. And now. And we can also ask about the density of the eigenvalues. So about the number of eigenvalues inside this shell. So if we move further from 0, there will be some non-zero density. Which is which will be proportional to the area of the sphere, and we can recover this result from this equality. So on the left hand side, we can say that this sum of lambda k e to the minus t lambda k can be approximated by the integral of some p of lambda, maybe f of lambda e minus t lambda d lambda when t goes to 0. And on the right hand side, it will equal to volume of the manifold of divided by 4 pi t to d over 2. And comparing comparing the left hand side and the right hand side, we can conclude that f of lambda when lambda goes to infinity is proportional to lambda to d over half minus I think minus 1. So yeah, like this times volume of manifold times times some number, and so it's true. It's true not only for this flat case, but for arbitrary manifold, because this limit when t goes to 0 is the same for all manifolds, because it's some local behavior of the Green function. And this technique is also used when people want to compute some traces or determinants of some operators. So they write formulas like this and then compute expansions of the hit kernel when t goes to 0. And, and sometimes there are situations when there are some objects that this quantities do not depend on t, and for example, when we send t to infinity, it gives some topological property. Like it should be some different version of Laplace operator, for example, using trivial connection. And we can, on one side, we can send t to infinity and compute some topological property which knows only about zero modes of some good operator, and on the other side we can send t to 0 and perform such a local computation, and it gives some index theorems, for example. Okay, so thanks for the attention. Next time I will derive some of these equations and tell about the other kind functions. Okay. Thanks.